Here we have the grand finale of a lot of the things that we've been working on. You're going to see a whole bunch of stuff come together in these next 3 sets of slides. The bad news is this particular video will be a little bit long, so use that pause button judiciously. The good news is the 2 follow-up videos will be pretty short. So we're going to look at linear transformations and eigenvectors. Now this sounds terrible, right? Those are horrible words. An eigenvector, what the heck is that? Well, we're actually going to look at 3 different eigenthings, eigenvalues, eigenvectors, and eigenspaces. Eigenvalues and eigenvectors are coming right up. Linear transformations, more Star Trek language. The definition we're going to work with is a pretty simple one, and here it is. A linear transformation is a matrix. That's it. There are other deeper definitions of linear transformations, but this is the one we're going to get away with for now. Okay, that's all. A matrix is a linear transformation. Here's why. Think about matrix multiplication of a vector. So take an m by n matrix A and a vector x, which would have to be n by 1 for the multiplication ax to work. What's the resulting size of this multiplication? It's m by 1. And so what has happened? This matrix A has acted on a vector x, which is n-dimensional, and it's turned it into an m-dimensional vector. Or it has, transformed the vector. Everything to do with matrices so far has been linear because matrices are coefficient matrices of some linear system of equations. So everything dealing with this is linear. So linear transformations. In the particular case when our matrix A is square, n by n, it will just take an n-dimensional vector. When we do ax, it will return another n-dimensional vector, by which it might rotate it, it might translate it, it might reverse its direction, it might just change it randomly, who knows. But the job of A is to transform the vector x, and you can design A to do some of these jobs specifically. We won't get into that, but in other classes you might. Now, what are these eigenvalues and eigenvectors? Well, eigen is German for distinctive, and so we're looking for distinctive values and distinctive vectors. So vectors and values that are special in some particular sense, and here's what we're looking for. We are going to look for scalar values of lambda and vectors v that, when coupled with a square matrix A, make this happen. In other words, A is trying to transform the vector v. Well, what happens to v? All it does is it changes v into a stretched, shrunken, reversed version of itself. So if lambda is 1, AV is equal to v, meaning A, the linear transformation, acts on v and does nothing to it. If lambda is 2, A acts on v and it produces something that's twice as long as v but has the same direction. So v is almost resisting the influence of this A, because the worst thing that the matrix A can do to v is stretch it or shrink it or reverse its direction. It can't change it terribly significantly. When this happens, we say that lambda is an eigenvalue of the matrix A and v is the corresponding eigenvector. Here's how this works in action. Here's a matrix A and a vector v. We can multiply them. We will produce the vector 0, 2, 6. And note that that new vector 0, 2, negative 6, is just 2 times the original vector. And so A acted on v and it returned 2 times v. And that's it. That's how we see an eigenvalue and corresponding eigenvector in action. We would say here that lambda equals 2 is an eigenvalue of A with corresponding eigenvector 0, 1, negative 3. Now we say it's an eigenvalue, which implies maybe there are others. And that's an interesting question, isn't it? So here's a list of things that are true about eigenvalues. For example, only square matrices are going to have eigenvalues. An n by n matrix will have n eigenvalues. Some of them may be repeated, so you might see 3 distinct ones, you might see 1 get repeated, but you know what that's like. You've found repeated roots in the past when you've done algebra, so that shouldn't freak you out. We would like to find the eigenvalues all at once, not search for them one at a time, and we will come up with a system. This system will also produce for us the corresponding eigenvectors, and this is where stuff that we've done before starts coming together. To find eigenvalues, we're going to set up a particular determinant and run it through with some algebra, and then to determine the corresponding eigenvectors, Yes, it's going to return us to solving systems of linear equations. But apart from the new terminology, you still should be in your comfort zone. So here's how eigenvalues and eigenvectors get discovered. The top line there is just the eigenvalue-eigenvector equation that defines what those mean. We're going to push everything to the left-hand side, just like we were going to find roots of an equation. You move everything to the left-hand side and you collect your terms and you do some factoring. So here we've done some matrix factoring, which is a little strange because note we've had to introduce the identity matrix. A minus lambda I is the collected coefficient of the vector v. And we want this to work, right? We're looking for values of lambda and the corresponding v's that make the top equation and so also the bottom equation work. Now the bottom equation represents a system of equations. How can we tell if that system of equations is going to work, i.e. is going to have a solution? Well, if the coefficient matrix has an inverse. How do we test if a matrix has an inverse? You test its determinant. So here's how it's going to go. We're going to take a matrix A and we want its eigenvalues. We're going to build A minus lambda I. Now I has to be the right size. If A is 2 by 2, then you use the 2 by 2 identity matrix here. If A is 3 by 3, you use the 3 by 3 identity matrix and so on. You're going to find the determinant of this mystery A minus lambda I. That determinant will have lambdas in it, and you will set the determinant equal to 0 and use your massive library of algebra skills to uncover the values of lambda that make the determinant 0. These eigenvalues can end up being real or complex numbers. We're going to be solving equations, possibly quadratic equations, cubic equations. You never know what's going to happen. Having found out what those eigenvalues are, then we're going to move to finding their partner eigenvectors. We will return to our friend A minus lambda I. We're going to make up an unknown eigenvector, and we'll just call its components v1 to vn in the meantime. And we want to load it up and discover, with a particular eigenvalue in mind now, again, how does this system work out? Well, this system is a homogeneous system of equations, so we know we're either going to get the trivial solution of just 0, or we're going to get an infinite number of solutions for the unknowns, which are v1 through vn, the components of v. Well, if we have an infinite number of solutions to pick from, we pick one, and that will become the eigenvector that goes with the eigenvalue lambda. Here's an example. It's 2 by 2. We're going to find the eigenvalues first. We're going to build A minus lambda I. So lambda times I is lambda times the identity matrix. You can see it there in the middle. And then A minus lambda I produces the matrix on the right. We're going to find the determinant of this matrix. Now you've done determinant, so I'm skipping some details here. But it becomes a quadratic equation, which is factorable. That's nice, at least in this case. And so we can discover that lambda equals 1 and lambda equals 2 are the two values which make the determinant of A minus lambda I be 0, which means those are the two values that make A times some vector v equal 2 times v. Now, what are those vectors v? So we're going to take the eigenvalues one at a time. Remember, they were lambda equals 1 and 2. We'll start with lambda equals 1. Here we're going to go back to our friend A minus lambda I and put in 1 for lambda. And we'll get this new matrix on the right, the negative 15, 12, negative 20, 16. We're going to construct A minus lambda I times the unknown eigenvector v equals 0. We want this to have a solution that we can find for v1 and v2. Now here's the reduced coefficient matrix. We've done row reduction here. Again, details are skipped because you know how to do this, but negative 15, 12, negative 20, 16 reduces with Gaussian elimination to this new matrix 1, negative 4/5, 0, 0. This tells us about our solutions for the unknowns v1 and v2. And remember, the right-hand side is 0, 0. So if this was an augmented coefficient matrix, there would be a right-hand column of zeros, but we don't really need to see it there. Okay, so this tells us something about the solutions for v1 and v2. It tells us there's an infinite number of solutions, which means we get to pick one as a free parameter. Let's choose v2, and if we choose v2 as the free parameter, call it t, then v1 becomes equal to 4/5 t by that top row. So here's our infinite number of solutions. We can pick any one of them to be the eigenvector, and in particular, I would like to choose the one with t equals 5 to get rid of that fraction. And so we will say that an eigenvector that goes with the eigenvalue lambda equals 1 is the vector 4, 5. Now we move over to our next eigenvalue. We're going to do exactly the same thing. We're going to build a minus lambda I. We're going to solve for the unknown vector v in the equation that's built out of the eigenvalues and eigenvectors. We'll find an infinite number of solutions, and you pick one. Now, I'm not going to show the details because I just showed you the details for lambda equals 1. I challenge you to pause the video at this point because you're probably tired of me now anyway at this point. Pause this, give it a shot yourself, and make sure you can come back with the vector 3, 4. Moving on, let's scale it up and do an example for a 3 by 3 matrix. We're going to find its eigenvalues and eigenvectors. The procedure is exactly the same. We're going to construct the determinant of A minus lambda I. So this is the coefficient matrix A minus lambda times the identity matrix that's 3 by 3. So you'll get collected terms down the diagonal. Now that determinant's a mess. It turns into the expressions on the right, which factors all the way down. And oops, I noticed there's a missing parentheses there in the middle. But you get a factored form of this determinant. Now, when you're doing determinants at this point, use a calculator, use Wolfram Alpha, go hop on Maple if you have access to it. Do whatever it takes. Right now, the important thing is the setup of the determinant, not the manipulations in the middle to get it solved. But having found the factored form of this determinant, we now know that the determinant will be 0 when lambda equals 5, 5 again, and 1. So one eigenvalue is repeated, no big deal. We would say it has multiplicity 2. There is a consequence of that will come out when we're finding eigenvectors, but it's actually helpful. But there are our eigenvalues for this matrix. To find the corresponding eigenvectors, we're going to go back and set up A minus lambda I times the mystery eigenvector v is 0 for each eigenvalue one at a time. So when lambda is 5, let's go back to the previous slide. So there's the determinant of A minus lambda I there in the middle. Imagine plugging in a 5 for lambda. Down the diagonal, you're going to get -2, -2, 0. Right, and so there we go. There's A minus lambda I times the unknown eigenvector equals 0. We want the solutions for this system, which can come from doing Gaussian elimination on the coefficient matrix. There is the fully reduced form. And what this tells us is that there are 2 free parameters in this solution space. There's only one row with anything in it. So the bottom 2 rows tell us that both v2 and v3 will be free parameters. So let's name them t for v3 and s for v2. The top row tells us that v1 equals negative v2, which means v1 is negative s. And so the eigenvector solution space structure is negative s, t. Now we can unwrap that into vectors, which are each multiplied by s and t. And what happens here is now we've discovered a pair of potential eigenvectors that correspond to the eigenvalue lambda equals 5. And so lambda equals 5 was repeated. It had multiplicity 2, and we came up with 2 eigenvectors to go with it. That's pretty cool. Now we go back and try lambda equals 1. There is lambda equals 1 plugged into A minus lambda I on the left, the matrix, and then the unknown eigenvector v in the middle, and the right-hand side of 0. Do full row reduction on the coefficient matrix. This one tells us in row 2 that v3 is 0, which means that v2 must be the free parameter, and the top row tells us that v1 equals v2. And so TT0 is the structure of the solution space here. Factor off the t, and that 1, 1, 0 makes a really nice eigenvector. This is the summary of the results we just got. We started with the matrix A. We found an eigenvalue set of 1, 5, and 5. 5 was repeated, so the eigenvalue lambda equals 1 gave us 1 eigenvector. The eigenvalue lambda equals 5 that was repeated twice gave us 2 eigenvectors. And so, ta-da, we had a 3 by 3 matrix. We found 3 eigenvalues. sort of, and we found 3 eigenvectors. So we found them all, and that's it.